we got a brief introduction about Taylor series and we are going to apply Taylor series now. So our question is, find ln 1.5 accurate to 0.001. So in this purpose, we have to find a function such that we will use this Taylor series to apply to find ln 1.5. We can use ln x for this fx equal to ln x. But there's a problem. If we are using this Taylor series to find that answer, we will see some problem in this remainder part. So we need to find accurate to 0.001. The remainder, the error of the approximation should be small as much as possible, which should be less than 0.001. So if we are finding that the remainder should be so much smaller, the remainder should be smaller. There is a term we say range of convergence of x. So in this case, actually the range of convergence of x is modulo x less than or equal to 1 greater than minus 1. So we say if x is in this region only, we can find this answer to this particular problem in this direct manner. Using this function only. It's because if we use something more than 1 or less than minus 1, this part, the Taylor polynomial, will not be a converging series. It will be a diverging series. If it is a diverging series, we cannot find. We have to find n. This is the approximated part for us. We have to find n such that we are approximating to a certain extent. We cannot find n if x is not in that region, if this diverges, because if this diverges, this won't be coming smaller. This should be, this should be converged to 0 actually. We will study that later. This part should be converging to 0 to find that approximation, so that only we can find appropriate n for our approximation. So we'll study that part later. So we'll just get an idea of Taylor series. So for that purpose, if we put ln x, the x will be 1.5 for our purpose. So that only we are using 1 plus x, ln 1 plus x. If we use ln 1 plus x, you can use any value that as we use in that range, the x should take that range. You can use 0.8 plus x or 1.2 plus x. If x, what we need is the x should be in that region. So we are taking, for convenience, we are taking ln 1 plus x. Okay, we got the function now. So we are given accurate to 0.001. So our reminder, this is the error for our problem. This error should be less than that part, 0.001. So let's say, can we use fx, can we use Taylor series for this part? Absolutely yes. This is n plus 1 times differentiable. So we can use Taylor series for this fx. So for the first, we will find the derivatives of fx. Right, fx equals ln plus 1, ln 1 plus x. F dash x equals 1 over 1 plus x. F twice x equals minus 1 over 1 plus x whole thing squared. F thrice x equals minus 1 into plus 1 into 2 over 1 plus x whole thing cube. So it is something we can get a pattern here. So the pattern we get is f n plus 1 x equals minus 1 to the power n times n factorial over 1 plus x to the power n plus 1. So we get the fact f n plus 1 x equals minus 1 to the power n into n factorial over 1 plus x to the power n plus 1. We are going to use this fact in proving this one. Okay, let's say what we need to find is this is r n x comma a. This is t n x comma a. So we need to find a also. There is an a here. For our convenience, usually in our problems, our semester problems, usually we use a as 0. A as 0. We can use other values also, but if we use a equals 0, the part will be more convenient. We use a0 in most of our problems, but if they are asked to find the solution at some other points, we should use other points to get the solution. So we use a equals 0, so our remainder can be written as Rn. We know the x value is 0.5 actually, 0.5 comma 0. The modular value of the remainder, it can be more, the actual value can be more than the approximated value, or it can be less than the approximated value. Okay, so our remainder is fn plus 1 zeta, and of course we know that about zeta. What is zeta? Zeta is something in between a comma b, that is 0 comma 0.5. We will be using this fact actually. So zeta is something in between 0 and 0.5. So there is a zeta which gives us the remainder fn plus 1 zeta. So we can use that formula, that notation. Fn plus 1 x is minus 1 to the power n into n factorial over 1 plus zeta to the power n plus 1, the modular value, into here we have x minus a to the power n plus 1. So we can write that as 0.5 to the power n plus 1, because our a is 0 and x is 0.5, and then n plus 1 factorial. The modular value. Since we are given to find up to 0.001, our error should be less than 0.001. Okay, now we will simplify this. We can cancel out and get an n plus 1 here, and this part goes off because everything will be the positive, and finally we get 1 over 1 plus zeta to the power n plus 1 into 2 to the power n plus 1 into n plus 1. This should be less than 0.001. Okay, but we don't know zeta. How to find zeta such that this approximation, the part what we are going to find is n, because if we find the n, how many times we have to iterate the Taylor series to get such an approximation? If we find n, we can directly use that n here to get that approximation. Actually, this is the one what we need to answer. For the answer, we need this one. Okay, so we need to find n, but zeta is something unknown. We know that zeta is in between 0 and 0.5, but we don't know what actually zeta is. But usually in these kinds of problems, we need to find an upper bound or the required bounds. If we bound this to some extent and use that one bound to a known value, actually if we can bound something here, a known value, what we know, and use that if this part, the known value is less than 0.001, actually this will be less than 0.001. So what we need is something to be bounded, to be inserted in between this inequality. Okay, let's see how can we use, this is something we can find using equations. So this is not a matter for us. This is the thing, 1 plus zeta. We can, I'll raise this one. usually in usual problems this bounding part happens for us. So it will be useful if we know how to bound a function to some extent, upper bound or a lower bound. So we can see zeta is something less than 0.5 and greater than 0. We can derive from that 1 plus zeta is less than 1.5 and greater than 1. Okay, so but we need 1 over 1 plus zeta. So 1 over 1 plus zeta is this is actually 2 by 3. Sorry, 3 by 2. 1 over 1 plus zeta will be greater than 1, sorry, less than 1 and greater than 2 by 3. Okay, we got a boundary here. The 1 over 1 plus zeta is less than 1 and it is greater than 2 by 3. For any zeta in this range, we got these values. It should be in between 1 and 2 by 3. Since these are positive values, this part should also be positive. So we can have the power n. So this should be less than 1 to the power n, that is 1, and this should be greater than 2 over 3 to the power n. Okay, now almost we are done with it. So we can use n plus 1, sorry. We need n plus 1. Okay. We got an upper bound here. So let's say this part we can, for a while we'll erase this one, and this part for all values of zeta in this range we have this is less than 1 into 1 over 2 to the power n into n plus 1. Okay, so we got an upper bound now, right? 1 over 1 plus zeta, since it is less than 1, we substituted that with an inequality. So if we find an n such that this is less than 0.001, obviously this one will be less than 0.001. So our remainder will be less than 0.001. Actually, easily we can find this part, 2 to the power, we can rewrite that part into 2 to the power n into n plus 1 greater than 1000, cross multiplying. We can use calculators to find n here. If we find n, the n will be something like, I'm not sure about the value. So the minimum value that n could have will be 7. The minimum value, minimum value the n could have is 7. We can use any n value which is greater than 7, but it's better to use the minimum value so that we can get a proper approximation as per to our question. So okay, we are done with n equals 7. So we got our remainder part and then simplified that. We got an upper bound and then we put that our needed required error value to that upper bound and find the n value, the minimum value of n. So now what we need to find is the approximation, the final answer. According to our Taylor series, this part is the remainder. Since we are given that remainder should be accurate to 0.001, we got n value. If we substitute directly n to here, then we'll be done. Let's see. So fx approximated will be that is actually Tn x 0.5 comma 0. That is what we need. This will be k equals 0 up to 7 f dash k is actually this one. Fk 0 is actually this one. We have minus 1 to the power k minus 1 into k minus 1 factorial over 1 1 plus zeta, it is 0. 1 plus x. Sorry, wait. 1 plus 0.5 to the power n dx. Yeah, 1 plus zeta, it means 1 plus x. The x part we need is 0.5, and then x minus a 0.5 to the power n over k factorial. That's k factorial. So this should be 0. We got 0 here. So this should be 0. This is equal to, I mean, this is the Taylor function actually, Taylor polynomial. If we put 0 here, for 0, we know that ln x, it's the function itself, it comes for 0. So for that, we'll take 0 out of here and put k equals 1. If we substitute 0 to this function, we get ln 1 plus 0, that is ln 1, that will be 0. So we got the 0 part plus summation of this thing. If we look for the summation directly by the calculator, we get 0.40 or something, and this will be our answer for the problem.